Across continents and millennia, humanity has gazed upon the colossal achievements of ancient civilizations and asked a single, persistent question: how did they do it? From the towering pyramids that pierce the desert sky to the perfectly interlocked stones of mountain citadels, these structures defy easy explanation, particularly when considering the supposed limitations of their eras. This investigation seeks to probe the evidence, examining the theories put forth by archaeologists and engineers to decipher the methods behind the impossible constructions of our ancestors. What kind of knowledge, what level of organization, and what technological prowess were truly available to these ancient peoples? Many of these constructions seem to demand a mastery of physics, mathematics, and logistics that we often associate with much later periods. We will examine the most compelling structures, scrutinizing the archaeological record, and considering the prevailing hypotheses. Our goal is not to find sensational answers, but to follow the factual trails, however faint, that reveal the genuine ingenuity of human history. Our journey begins with arguably the most iconic ancient marvel, the Great Pyramids of Giza. Constructed around 2580 to 2560 BC, these colossal tombs remain an enduring symbol of ancient Egyptian power and engineering skill. The largest, the Pyramid of Khufu, is estimated to contain over 2.3 million stone blocks, some weighing upwards of 80 tons. The sheer scale of this undertaking prompts fundamental questions about the techniques employed by the Old Kingdom Egyptians, who possessed no iron tools, no wheeled vehicles for heavy transport, and no pulley systems in the modern sense. Archaeological evidence suggests that the stone for the pyramids came from several locations. Local limestone was quarried directly at Giza for the bulk of the structure, while finer Tara limestone for the casing stones was transported across the Nile. Granite, used for the king's chamber and other internal structures, came from Aswan, hundreds of kilometers to the south. Researchers like Dr. Zahi Hawass indicate that copper chisels, stone hammers, and wooden levers were the primary tools used to extract these massive blocks, a painstaking process demanding immense labor. One of the most debated aspects is the transportation of these massive stones. For granite blocks from Aswan, river barges were almost certainly employed, leveraging the annual Nile inundation. However, moving blocks from the quarries to the construction site, especially the heaviest ones, remains a topic of considerable study. Dr. Mark Lehner's ongoing excavations at Giza have uncovered a sophisticated harbor system, suggesting an intricate network of canals and docks brought materials remarkably close to the plateau. For overland transport, one prominent theory, supported by a 2014 study by physicists at the University of Amsterdam, involves wetting the sand in front of wooden sledges. Their research suggested that adding a small amount of water to the sand could have the number of workers needed to pull a sledge. This simple yet ingenious technique would have significantly reduced friction, allowing hundreds of men to move enormous stones across the desert floor more efficiently than previously imagined. Once at the base, how were the blocks lifted hundreds of feet? The consensus among Egyptologists, including Jean-Pierre Adam, is that various types of ramps were used. Theories range from a single, straight ramp to a spiraling ramp wrapping around the pyramid, or even internal ramps discovered by architect Jean-Pierre Houdin. Experimental archaeology projects have attempted to replicate these methods, demonstrating that even with basic tools, it is plausible to hoist these stones using human and animal power, levers, and counterweights. Beyond sheer scale, the precision of the pyramids is astounding. The Great Pyramid's base is almost perfectly square, with sides aligned remarkably close to true north, south, east, and west. Flinders Petrie's measurements in the late 19th century highlight deviations of mere centimeters. This accuracy suggests a profound understanding of astronomy and surveying. Scholars like Kate Spence propose that early Egyptians used two stars, Ursae Majoris and Ursae Minoris, to establish a true north alignment, particularly around 2467 BCE, a period consistent with pyramid construction. For decades, popular culture depicted pyramid builders as enslaved laborers. However, archaeological findings, particularly the discovery of workers' villages by Dr. Zahi Hawass and Dr. Mark Leiner, paint a different picture. These settlements reveal bakeries, breweries, and cemeteries for workers, indicating a large, organized, and well-cared-for workforce, likely composed of skilled craftsmen and temporary laborers, often farmers, contributing during the Nile's flood season. This suggests a highly sophisticated state-organized project, not just brute force. Shifting continents and millennia, we arrive at another monumental mystery, Stonehenge, standing majestically on Salisbury Plain in England. Constructed between 300 and 1500 BC, this prehistoric monument of massive sarsen and bluestone megaliths represents an extraordinary feat for Neolithic and Bronze Age peoples. Unlike the pyramids, Stonehenge's purpose is largely debated, but its construction techniques, particularly the movement and erection of its stones, pose a unique set of challenges to modern understanding. The stones of Stonehenge are of two main types, the larger sarsens and the smaller bluestones. The sarsens, weighing up to 30 tons, are local, found within 30 kilometers. The bluestones, however, weighing 2 to 5 tons each, present a far greater puzzle. Geological analysis confirms their origin in the Preseli Hills of Wales, some 250 kilometers away. This incredible distance, especially for stones moved over rough terrain, rivers, and potentially by sea, highlights the immense dedication and engineering prowess of its builders. The most widely accepted theory for bluestone transport involves a combination of land and water routes. Archaeologist Mike Parker Pearson and his team suggest that the bluestones were moved overland from the Preseli Hills to Milford Haven, then loaded onto boats or rafts, ferried along the Welsh coast, up the Bristol Channel, and finally up the River Avon. From there, they would have been dragged overland again to the Stonehenge site. This monumental journey speaks to a sophisticated understanding of logistics and collaborative effort. Once at the site, the challenge shifted to raising these massive stones. Experimental archaeology, led by teams like those at English Heritage, has provided plausible methods. One primary theory involves digging a large pit with a sloped side, then using ropes and leverage to pull the stone upright into the pit. For the lintel stones placed horizontally, a system of timber cribs or ramps, gradually built up around the uprights, would have allowed the stone to be slid into place. These methods, while labor-intensive, require no supernatural technology. Perhaps one of Stonehenge's most surprising features is its sophisticated joinery. The upright sarsen stones are topped by horizontal lintels, which are secured using mortise and tenon joints, a technique typically associated with woodworking. Additionally, tongue and groove joints connect adjacent lintels, forming a continuous ring. This demonstrates a remarkable level of planning and craftsmanship for a Neolithic society, suggesting a highly skilled workforce, capable of precise stonework using only rudimentary tools such as stone hammers and antler picks. While its exact purpose remains debated, many scholars, like Gerald Hawkins, propose Stonehenge served as a sophisticated astronomical observatory or calendar. Its alignment with the summer solstice sunrise and winter solstice sunset is undeniable, suggesting an intimate knowledge of celestial movements. This astronomical precision, achieved without written language or advanced instruments, points to generations of careful observation and the transmission of complex knowledge, embedding scientific understanding within a monumental structure. From the enigmatic circles of Stonehenge, we turn to the vast, enduring empire of Rome. While perhaps less mysterious in their methods than earlier civilizations, the Romans achieved engineering feats of unprecedented scale and longevity, largely due to one innovation: concrete. Roman concrete, or opus caementitium, allowed them to construct structures that have withstood millennia, often surpassing the durability of modern concrete, whose foundations are still being studied today. The key to Roman concrete's extraordinary durability lies in its unique composition, specifically the inclusion of volcanic ash, known as pozzolana. Unlike modern concrete, which relies on Portland cement, Roman concrete was a mixture of volcanic ash, lime, and rock aggregate. Professor Marie Jackson's research at the University of Utah has revealed that reactions between the volcanic ash and seawater in coastal structures created a robust, self-healing material, forming rare aluminum tobermorite crystals within the concrete matrix. The Pantheon, completed around 126 AD, stands as a crowning achievement of Roman concrete technology. Its massive dome, spanning 43.3 meters, remains the largest unreinforced concrete dome in the world. The engineering strategy involved gradually lightening the concrete mixture as the dome rose, using lighter aggregates like pumice at the apex. This innovative approach, combined with precise geometrical calculations, allowed for a structure that has endured for nearly 2 millennia without collapsing. The Roman aqueducts are another prime example of their practical engineering genius. Designed to supply cities with fresh water, these vast networks stretched for hundreds of kilometers, employing gravity to maintain a constant, gentle flow. The Pont du Gard in France, for instance, exhibits extraordinary precision, with a gradient of only 34 centimeters per kilometer, or 1 in 30,000. This required meticulous surveying and construction over varied terrain, utilizing tunnels, bridges, and siphons to maintain the necessary slope. The success of Roman engineering wasn't just about materials, it was also about unparalleled organization. The Roman army often played a crucial role in large-scale construction, providing skilled engineers, surveyors, and a disciplined labor force. Furthermore, standardized building practices, widespread use of concrete, and a clear chain of command allowed for the efficient execution of massive infrastructure projects across a sprawling empire. This demonstrates a state-level commitment to public works, unmatched until much later periods. Our final destination takes us high into the Andes Mountains, to the astonishing stonework of the Inca Empire. Sites like Sacsayhuaman and Machu Picchu showcase a unique architectural style where massive, irregularly shaped stones are cut and fitted together with such precision that not even a knife blade can pass between them. This technique, known as ashlar masonry, was achieved without mortar, and the earthquake-resistant properties of these structures continue to impress modern engineers. The sheer scale of some Inca blocks, weighing many tons, necessitates an explanation for their quarrying and shaping. Archaeological evidence suggests that the Inca used a method known as percussion flaking for shaping, employing harder stones like diorite and hematite as hammerstones. For quarrying, wedges likely made of wood were driven into natural fissures and soaked with water to expand, cracking the stone. This painstaking process would have required immense patience and a vast workforce. Transporting these colossal blocks over mountainous terrain remains a primary challenge to researchers. Scholars propose various methods, including rolling stones on logs, dragging them on ropes across greased ramps, or using earth ramps and levers. For example, some stones at Sacsayhuaman originated from quarries several kilometers away and hundreds of meters lower in elevation. The logistics of moving these giants uphill, often around sharp bends, points to an incredibly disciplined and ingenious labor force, utilizing simple machines to their maximum potential. The most baffling aspect is the near-perfect fit of the irregular stones. Theories suggest a process of trial and error, where stones were repeatedly fitted, removed, and ground down using sand and water until a perfect interlock was achieved. Some propose that bosses or protrusions left on certain blocks were used as handholds for positioning, later removed. This exactitude not only created aesthetically pleasing walls but also provided incredible seismic stability, as the interlocking stones could shift slightly during earthquakes and then settle back into place. Machu Picchu itself is a testament not just to stonework but to integrated engineering with its environment. Built on a narrow ridge between two peaks, its terraces prevent erosion and provide agricultural land, while sophisticated drainage systems channel rainwater away from structures. The city's construction demonstrates a deep respect for and understanding of its challenging mountainous topography, turning natural obstacles into structural advantages. This holistic approach is a hallmark of Inca engineering, often overlooked in favor of the impossible stone fits. It's crucial to acknowledge that for many ancient constructions, the historical record is incomplete or entirely absent. This naturally leads to differing interpretations among experts. For instance, while most archaeologists agree on ramp systems for the pyramids, the exact configuration of these ramps remains a subject of active debate, with no single, universally accepted model. Our understanding is often built upon inferential evidence, experimental archaeology, and careful interpretation of subtle clues left behind. In the absence of clear answers, some alternative theories gain traction, particularly those suggesting extraterrestrial involvement or lost ancient supertechnology. While such ideas capture the imagination, rigorous investigative journalism demands adherence to verifiable evidence. To date, no credible archaeological or scientific evidence has been presented to support these claims for any of the structures discussed. The current body of research consistently points towards ingenious human solutions, albeit ones that challenge our modern preconceptions about ancient capabilities. What emerges from our investigation is a consistent picture. The impossible was achieved not through forgotten superpowers or extraterrestrial aid, but through immense human ingenuity, persistent experimentation, and highly organized collective effort. These civilizations leveraged a profound understanding of basic physics, observed astronomical cycles, developed sophisticated logistics, and mastered the materials available to them. Their technology was often simple tools amplified by massive, coordinated labor. Each civilization demonstrated a unique mastery of its local materials. The Egyptians understood the properties of limestone and granite, shaping them with copper and stone. The builders of Stonehenge had a deep connection to sarsen and bluestone, recognizing their structural potential. The Romans revolutionized construction with their volcanic ash-based concrete. And the Inca transformed the Andean landscape using precisely cut and fitted local stone. This intimate knowledge of geology and material science, acquired over generations, was foundational to their architectural success. The scale of these projects also underscores the advanced organizational and social structures of these societies. Building a pyramid, an aqueduct, or a mountain citadel required centralized authority, efficient resource allocation, and the ability to mobilize and sustain a large workforce for decades. This speaks to sophisticated governance, administration, and social cohesion. It was not just about knowing how to move a stone, but having the societal framework to make hundreds of thousands of such movements happen. How was such complex knowledge transmitted across generations without extensive written records in many cases? It likely involved a strong tradition of apprenticeship, oral histories, and practical, hands-on learning. Skills were passed from master to apprentice, perfected over centuries, much like ancient craft guilds. This institutionalized knowledge transfer ensured that highly specialized techniques, from quarrying to precise masonry, were preserved and improved upon, allowing for ever more ambitious projects. Finally, we must consider the immense luxury of time. These ancient projects were not built to modern schedules. The Great Pyramid took an estimated 20 years. Stonehenge evolved over 1,500 years. The Roman aqueducts were continuously built and maintained over centuries. This dedication, spanning generations, allowed for monumental tasks to be broken down into manageable steps, relying on consistent effort rather than sudden technological leaps. Their ambition was matched only by their patience. Our investigation reveals that the impossible constructions of ancient civilizations were, in fact, triumphs of the possible. They stand not as mysteries begging for supernatural explanations, but as profound testaments to human potential. These structures remind us that given sufficient resources, collective will, time, and ingenious application of fundamental principles, humanity has always been capable of astonishing achievements, pushing the boundaries of what is considered feasible. What lessons can we draw from these ancient builders? Perhaps it is the importance of understanding our materials, working harmoniously with our environment, and the incredible power of collective human effort directed towards a common goal. They did not have our machines, but they possessed an invaluable combination of empirical knowledge, organized labor, and profound vision. Their legacy challenges us to look beyond immediate technological limitations and to reconsider what can be achieved with ingenuity and perseverance. The story of ancient engineering is far from complete. New archaeological discoveries, advancements in scientific analysis, and innovative experimental archaeology continue to refine our understanding. As we continue to probe these enduring wonders, we gain not just insights into ancient techniques, but a deeper appreciation for the enduring human spirit of creation and ambition. The stones still stand, silent witnesses to their builders' brilliance, waiting for us to uncover more of their secrets.